Welcome back. So today we're going to look at some parallel sorting algorithms. So we're going to look at four algorithms. So the first one is going to be radix sort, and then we'll look at parallel merge sort, and then we'll look at something called bitonic sort, and then sample sort. Okay, so to start out with, we're going to talk about radix sort. Okay, so this is actually a sequential sorting algorithm. But it turns out that you can run this very efficiently in a parallel setting also. Okay, so radix sort, so the word radix just means digit. Okay, so radix sort is just sorting numbers digit by digit. Okay, and we're gonna sort from the least significant digit up to the most significant digit. Okay, so for example, over here, right, you've got a bunch of numbers that we're trying to sort, let's say in increasing order. And then, so first of all, we're going to sort the least significant digit, the ones digit, in increasing order. Okay, and then next, you're going to sort the next digit, the tens digit, in increasing order, and then you sort the hundreds digit in increasing order. Okay, so that's radix sort. Now, one important thing is that when you do these sorts, okay, they have to be stable. So stable means that if you're sorting on a current on some digit, okay, let's say the hundreds digit, okay, then suppose there's a tie in this digit, all right. Then in order to figure out what order you should have, you need to preserve the order of the two numbers that are tied. You need to preserve the order from the previous digits. Okay, so as an example of this, suppose we're sorting on the hundreds digit over here, right? So, when you're sorting, you're going to get a tie on this on the threes over here. Okay, so in that case, you need to look back at the tens digit, and you need to see what order these two numbers are in. Okay, so on the previous digit, right, you have the 362 before the 397, and so here, when you have a tie, you need to maintain that order in order for the sort to be stable. Okay, so you need to keep 362 before 397. Okay, so that's the stable sort, right? And we have to use a stable sorting algorithm in order to implement radix sort. Okay, so I said this is a sequential sorting algorithm, but you can parallelize it. And basically, the reason is that when you sort on each digit, you can actually do this very efficiently in a parallel way. Okay, sorting digit by digit. And so, this leads to the fact that radix sort is often one of the fastest sorts in practice, okay, especially in the shared memory setting. Okay, all right, so, okay, so the way we're going to implement, so now we'll talk about how to implement radix sort in parallel, okay? And it turns out that we're going to make use of the parallel prefix sum operation. Okay, so remember from a few lectures ago, we talked about a number of applications for prefix sum. Okay, so this is yet another application for prefix sum, which is to do very efficient radix sort. Okay, all right. So what we're trying to do is so as long as we can sort one particular digit, of a set of numbers, okay, then we can just apply the same method to all the digits, and then we'll get a radix sort. Okay, so we'll just focus on sorting one of the digits of a set of numbers. Okay, and we're going to assume these are binary numbers. So all of the digits are zeros or ones. Okay, and we're just going to focus on sorting the last digit in a set of binary numbers. And we want to sort these in a stable way. Okay, so now since they're binary numbers, and if we're going to focus on the last digit, then the last digit is either going to be a 0 or a 1. Okay, and so we're going to call the values which end with 0, we're going to call them 0 values. And the other values which end with 1, we'll call them 1 values. Okay, so then if we're sorting on this digit, then since the only possible values for this digit are 0 or 1, all we need to do is put all of the 0 values before all of the 1 values. And we have to do this in a stable way. Okay, so all right, so then I'll show you an example of how this works. Okay, so this is much easier to explain with this example. All right, so suppose we're trying to sort these numbers over here. Okay, now we're just trying to sort them based on their final digit right now. So the first thing is, let's just pick out the final digits. Okay, so like this guy ends on a 0, so then we're going to pick out the 0. Okay, this guy ends on a 1, and this guy ends on a 0, and so forth. Okay, all right, so next we're going to take all these digits and we're going to flip them. Okay, so the 0s become 1s and the 1s become 0s. Okay, and we'll see why we do this later. Okay, so then that's going to produce this array of numbers. Okay, so we're trying to sort 8 numbers, and then we're going to take out the 8, the least significant digits, and then flip them. And so now we have this array of 8 numbers, and now we're going to do a exclusive prefix sum on these numbers. Okay, the flipped bits. Okay, so for example, the first value here, right? This is a 0 because if you do exclusive prefix sum, then the first value is always 0, right? And then here, this is going to be 1 because you're just taking this value, right? And then here, this is also going to be 1, so this is the sum of 1 and 0. This is a 2 here because it's a sum of 1, 0, and 1, right? And then you can see that the rest of these values here are just the prefix sum of this E array. Okay. All right. So why do we do this prefix sum? Okay. What's the use of that? Well, the use of that is now when you're sorting these 0 values and the 1 values, then the only thing you need to do, since there are only 2 possible digits, the only thing you need to do is put all the 0 values before all the 1 values. Okay. However, suppose you have a 0 value. Okay. So let's say that you have a 0 value at some index I. Okay. So for example, this is a 0 value over here. Okay. Now, where does this guy go after you sort him? Okay, so the claim is that the position that you should put him is equal to the number of 0 values that come before this index. Okay, so the number of 0 values before this position is, well, here's a 0 value and here's a 0 value. Okay, right? So both of these 0 values, since we're sorting in a stable way, both of these guys should come before this 0 value after the sort. Okay, so this is why this guy belongs in position number 2 at the end, because he's got to come after these 2 0 values. Okay, and so in fact, this D array here, okay, so I'll tell you later how I'll tell you exactly how we compute these values, but right now you see that the D here is a 2, and this is indicating that this guy belongs in position 2, okay, because there are 2 0 values before him. Okay. All right, so next, how do we know how many 0 values are before him, right? So of course, we could just scan through all of those values and count them, but that's very inefficient, and also that's not a parallel operation. Okay, so the way we can know that there are 2 0 values before him is using this F array. Okay, so you see that F here is exactly equal to 2. Okay, and the claim is that F exactly counts the number of 0 values before this position. And the reason for that is that the way we formed F was we did an exclusive prefix sum on E. Okay, and E is going to be 1 whenever there's going to be a 0 value before this position. Right, so like here we have 2 0 values before this position, and then we have 2 1s corresponding to those. Okay, and this 2 exactly comes about because you took the sum of these 2 1s. Okay, so this shows you that these prefix sum values, okay, they count up exactly how many 0 values come before a position. Okay, so as another example, right, right, if you take this position, okay, then the prefix sum here is 3, right, and that's because you have 3 0 values, okay, this guy, and that guy that come before this position. Okay, so to just say this again, whenever we have a 0 value at some particular index I, okay, then we should put this 0 values. So after sorting, we should put this 0 value at a position equal to the number of 0 values before index I. Okay, and the way you can know that number is that you can just look at the value of the F array at this position, and that tells you exactly how many 0 values are at this position. Okay, so now we know how to take care of all of the 0 values. Okay, we know exactly where they go. Okay, so so we know that so like here you have a 0 value, right? So it goes to 0, right? Because his prefix sum here is 0. This guy has a 0 value. He goes to 1, right? He goes to 2, And then the final zero value here, he goes to 3. Okay, so we're done with the zero values. And now we have to talk about the 1 values. Okay, so the 1 values is a similar thing. Okay, however, notice that the 1 values have to come after all of the 0 values. Okay, so we have to know how many 0 values there are, right? Because because even the smallest 1 value has to come after all of the 0 values. Okay, so then how do you know how many 0 values there are? Well, if you look at this prefix sum, okay, if you look at the final value here, right, what is this equal to? This is whenever there's a 0 value, there's a 1 here. So therefore, this thing is equal to the number of 0 values before this final position. Okay, and finally, there could be another zero value at this final position, right? So in this example, there's another 0 value at this final position. And so therefore, to get the total number of zeros, we're going to take the final f value, right, plus whether or not the final value was a 0 value or not. Okay, so we add these two together. Okay, so here you see that, it's going to be 3 plus 1. So we see that the total number of 0 values is going to be 4 here. So that means that all of the 1 values go after index 4. Okay, all right, so this is going to be 4 over here. And furthermore, if you have a 1 value at an index I, okay, then not only does it go after all the zeros, it should also go after all of the 1 values that come before index I. Okay, so this is just like, when you have a 0 value, it has to go after all of the 0 values that come before index I. Okay, here, this has to go after all of the 1 values that come before index I. Okay, so now, so when you wanted to get this value, the number of 0 values, you just looked at the f array, okay, the f values, okay. What about this? Okay, how do we know how many 1 values come before I? Well, the thing is that all the values before position I, they're either going to be 0 values or 1 values, okay. So if you want to know how many 1 values there are, you can just take this index I and subtract how many 0 values there are. That tells you how many 1 values there are. Okay, and we can find how many 0 values there are just by using this f array. Okay, so therefore we have this formula for the position that a 1 value should go to. Okay, it's equal to the total number of 0 values plus I minus the number of 0 values before position I. Okay, so as an example of how this works, so suppose you take this is a 1 value here. Okay, so let me erase some of this stuff. Okay, so it's a 1 value. So therefore, the position that it goes to is, we can do this calculation here. Okay, so first of all, the total number of zeros is going to be 4 over here, right? And the index is, so this is index number 5 over here, right? And then we need to subtract the number of 0 values, 3, right? So that indicates that there are 2 1 values before this position. Right, and those 1 values are this guy and that guy. Okay, so this is like the third 1 value, right? And then he also goes after the 0 values. So therefore his position is going to be this 5 minus 3 plus 4, which is position 6. Okay, this guy belongs in position 6 over here. Okay, and likewise you can do a similar computation for all of the 1 values. Okay, so that's basically the algorithm. Okay, so what we're gonna do is we're gonna first of all produce all of these bits. Okay, so obviously that is a parallel operation, right? And then next we're gonna flip all the bits, which of course is also parallel. We're gonna do the parallel prefix sum. Okay, so we saw a bunch of algorithms for parallel prefix sum. So this is a efficient and parallel algorithm, right? And then after that, now we can figure out where all of these values should be assigned in the final sorted order. Because anytime you have a 0 value, right, then you simply you use the f value to determine its position. And if you have a 1 value, right, then you're going to use this other formula to determine its position. Okay. And so yeah, and so that's what this thing is doing over here, right? It's saying that if the bit here is equal to 1, then you're going to, so this bit here, this B is referring to this array over here, okay? So it's saying that if you have a 1 in this in a certain position, then your sorted position is going to be, based on the 1 value, okay? So this formula for the 1 value, right? And then otherwise, it's going to be based on the formula for the 0 value, which comes from the F array, okay? So we can compute all of these D values in parallel, right? And that tells you the final position for each of these values. Okay, so for example, it tells you that this, the second input value 1, 1, 1 over here, it needs to go into position 4 in the final sorted order. Okay, right? This guy over here, right? He needs to go into position 1, right? So we're going to just move him to position 1, right? So by computing these D values, right, we can determine the final position for each of the input values. And then your final step is just to sort of scatter these input values using these addresses. Okay, so so all of the steps that we talked about, that they're all highly parallel, right? And then and the crucial thing was to do this prefix sum over here. All right, so so that's the basis for a an efficient radix sort algorithm. And this works quite well on shared memory settings and GPUs. Okay, so the next algorithm we're going to talk about is merge sort. Okay, but parallel merge sort. Okay, so we've all seen merge sort. So merge sort is just to remind you, you have this big array over here. So it's a divide and conquer algorithm. So you first chop up this array into halves. Right, and then you keep splitting this array until you're down to like subarrays of a sufficiently small size, right? And then you start merging these subarrays in sorted order. Okay, so like when you merge the 38 and the 27, you get you need to put them into sorted order. Okay, so these guys need to be sorted. All right, so then at each layer you have a bunch of these sorted subarrays. Okay, and at the next layer you're going to combine, you're going to merge 2 of these sorted subarrays into another sorted subarray. Okay, and then and then you just keep doing that. Okay, all right. So that's the sequential version of merge sort. So we have that if there are n numbers, right? Then we're going to do log n divide stages, followed by log n merging stages. Okay, and in a sequential setting, each stage takes order n time. Right, so altogether, it's going to take order n log n time. Okay. Now, in a parallel setting, we need to still do these divide and merge stages. Okay, the divide stages are easy to do in parallel, right? Because in fact, you don't really need to do anything. You just take part of the array. That's all you do. But what is not so obvious how to do in parallel is suppose you want to merge 2 arrays. Okay, so let's say you want to merge this array and this array. Okay, so that in a sequential setting, what we had were we had these pointers to these different arrays, and then we sort of move these pointers from left to right in order to merge these 2 arrays. Okay, but that's a sequential process, and so it doesn't seem obvious how to translate that into a parallel setting. Okay, so the main thing that we're going to do in order to implement parallel merge sort is we'll show how to do the merging stage. Okay, do each of these merging stages in order log n time when you have n parallel processors. Okay, so you have n numbers over here in total, right? And then we want to merge all of these sublists, and we'll see how to do this in log n time. Okay, if you have n processors. All right, so now each of these merging stages takes you log n time, and then you have log n of these merging stages. Okay, so so that means that in total, you're going to take log squared n time to sort using n processors. All right, now this is not quite efficient because the total amount of work that we're doing is going to be the number of processors times the time. Okay, so that's going to be n times log squared n. Okay, whereas in the sequential setting, our total work is n log n. Now, it turns out that there is a more complicated version of parallel merge sort, which does sort of pipelining. It sort of pipelines these merge operations. And by doing that, you can actually get the total work for this algorithm to be n log n. Okay, yeah, but we're not going to talk about that. But So we'll just talk about the simple version of this merge sort. And also, we're going to assume for simplicity that all the values are unique. Okay. So of course you can do this when you have non-unique values, but it's just simpler to assume all the values are unique. Okay, so let's talk about how to merge two lists of sorted numbers into a big sorted list. Okay, so suppose you have these two lists, right? So they're already sorted. Now we're going to define this thing called rank. Okay, so this is a value in a set. So the rank of a value in a set is like we're going to go look in the set and see how many values are less than or equal to x. Okay, so that is the rank of x in S. Okay, it's equal to the number of values in S less than or equal to x. So for example, if you take this 8 here, right, then the rank of 8 in A is going to be 2, right, because there are two values less than or equal to this guy. Okay. If you take 8 and you compute the rank in B, right, so there are 3 values less than 8, and so his rank is 3. Okay, and likewise, the rank of 20 in A is going to be 4, okay, because there are 4 values less than 20. Okay, so now we have this claim that suppose you take a number from either A or B, okay, and now suppose you combine A and B into a big list, okay, or into a big set, let's say, okay. Then the rank of this value x, which comes from A or B, right? The rank of it in the combined list A concatenated with B. Okay, this is going to be equal to the rank of x in A plus the rank of x in B. Okay, so as an example of this, suppose you want to do the rank of 8. Okay, in the overall list. Okay, so 8 in the overall list. So once you combine A with B, right, then 8 is going to be so there are like 5 values less than or equal to 8. Okay, and this happens to be equal to the rank of 8 in A, which is 2, right, and the rank of 8 in B, which is 3. Okay, all right. You know, likewise, if you do the rank of 20, right, so the rank of 20 is going to be 8 because you know the 20 is like the 8th value in this overall sorted list, and this is equal to the rank of 20 in A, which is 4, and the rank of 20 in B, which is also 4. Okay, so the reason for this claim is quite simple, right? Because if you take a number, right, let's say that it comes from A, okay? So then the rank of x in A is how many values are less than x in A, okay, including x itself, okay? Likewise, the rank of x in B is how many elements are less than or equal to x in B, okay? And since we're assuming that you know, all these values are unique, then you know so x cannot be if x is in A, then it's not in B. Okay. All right. So then the rank of x in A concatenated with B is just how many values are less than x in A plus how many values are less than x in B. Okay. So that's just the sum of these two ranks. So yeah. So that gives you so that shows the claim. All right, now this claim is actually pretty important because this is how we're gonna what we're gonna do to do the parallel merge sort. Okay. Now the only thing is how do you compute the rank of a value in a set? Okay. Now if this set is sorted, okay, and suppose it's got a size of n, right? Then you can compute this rank in order log n sequential time. Okay. So even if you only have one processor, right? If you have a sorted array of size n, you can compute the rank of x in S using just one processor in log n time. Okay, and the method is just you do binary search for x in S. Okay, so as you do binary search, right, then you're gonna sort of isolate where x can occur in S, and then the final position that you end up at, okay, the index, right, that is gonna be that's gonna tell you the rank. So either at this index, the value is equal to x, okay? In that case, the rank is going to be I plus 1. Or if it's not equal to x, the rank is going to be equal to I. Okay, and this binary search with one processor is going to take you log n time. So therefore, we can compute the rank of any number in any set of size n in just log n time using one processor. Right. Okay. So this is like an example of this, right? If you search for the rank of 11, if you do a binary search for 11 in this list, right, you're going to end up at this position over here. So it's going to end at index 3, and the rank of x is actually equal to 3. All right, so now we can put everything together, okay, into how we can implement parallel merge sort. Okay, or sorry, rather, now we're gonna do see how to implement parallel merge. Okay, once you have parallel merge, then you just get parallel merge sort right away. Okay, so if you want to do parallel merge, so what we're doing is we have two sorted arrays A and B. Okay, let's say they both have n elements. Okay, and now we're trying to merge them into one big sorted array, A concatenated B. Okay, and let's say that you're allowed to have 2n processors to do this. Okay, and now we claim that you can merge these two guys in log n time. Okay, and the way you do this is that what we're going to do is so we have 2n values overall, and you have 2n processors. So you assign one processor for each value. Okay, and for and the ith processor is going to take care of the ith value in the in array A. Okay, so we have I processors here, and sorry, we have M processors here, we have M processors here. Okay, so the ith processor in the A list is going to take care of the ith value here, and he is just going to compute the rank of this value in A and in B. Okay, so we're going to take the ith value from A and compute its rank in A and in B. Okay, well, now the rank of the ith value of A in A is simply its index itself. Okay, because the fact that it's at position I means that it's the ith largest value, because A itself is sorted. Okay, so rank of A of I in A is equal to I. And then rank of A of I in B, right, we can do that in log n time, just using the single processor using binary search, as we saw. Okay, so whatever this rank is of A of I in B, then the final rank of A in the overall list, right, then we can use the claim, the previous claim, to say that the final position of A of I in this overall merged list C is going to be the rank of A of I in A plus the rank of A of I in B. Okay, so likewise, we have a bunch of processors assigned to these B values, right? And for each of those processors, it's going to compute, so if it's a jth processor, it's going to be handling the jth B value, and it's going to compute the rank of B of J in B, which is just J, and it's going to compute the rank of B of J in A, which it does using binary search. Okay, and then we know that the final position that the jth value should go to is equal to J plus R of J. Okay, so as an example of this, right, if you compute the ranks of all of these values in in B, right, then these are the ranks over here. Okay, and these are the ranks of these values in A. All right, and now the positions that these guys should go into is, so for example, this guy has a rank of, he's got an index in A of 0, and he's got a rank of 0. Okay, so therefore he goes into index 0, right? This guy has a rank of 1 in A, and then he's got a rank of 3 in B, right? So he goes into position 1 plus 3, which is 4. Okay, so yeah, so you take these formulas and then you apply it to all of these things, and that tells you the final position of all these values in the merged list. Okay, and everything we're doing is parallelized, right? Because we just need to compute these ranks, and all of these just need one processor, and they can all run in parallel. And the running time is going to be log n. So therefore, we can merge these two lists in log n time. Okay, and so we can do parallel merge in log n time, and so therefore, in order to do merge sort, right, overall, it's going to take us, since we have log n stages of this, right, it's going to take us log squared n time to sort all the numbers. Okay, so that is parallel merge sort. Okay, so the next algorithm we're going to look at is called a bitonic sort. Okay, so bitonic sort, first of all, we're going to define this thing called a bitonic sequence. Okay, so bitonic sequence is, it's one of two things. Okay, either it's going to be a sequence that first increases and then decreases. Okay, so there are like sort of two phases to this. Like bitonic just means that there are sort of like two phases to the sequence. Okay, increasing phase and then a decreasing phase. Okay, or a bitonic sequence is a rotation of a sequence which first increases and then decreases. Okay, so let's see some pictures of these. Okay, so first of all, this is a bitonic sequence, right? This 1, 3, 4, 7, this thing, okay, because it first increases, right, and then it decreases. Okay, or you could take a rotation of the sequence. Okay, so for example, if you rotate everything to the left over here, right, so then these three values get shifted over to the end over here. So this is a left rotation of a increasing decreasing sequence. Okay, then this thing is also a bitonic sequence. Let's see. Okay, so actually let's look at this picture over here. Okay. Yeah, okay. So this picture, this shows what a bitonic sequence looks like. Okay, so this is the first kind of bitonic sequence is it first increases and then decreases. Okay, or you could rotate this guy, right? So when you rotate this guy, let's see. If you rotate this guy, so then yeah, so then if you take all this stuff, right, and then put it over here, so that it's over here, right? So then it becomes an increasing followed by decreasing sequence. Okay, so this thing on the bottom is a rotation of the thing on the top. Okay, so that's what a bitonic sequence is. And now we have the first property about bitonic sequences, which is that suppose you do this operation. Okay, suppose you have a bitonic sequence like this with n numbers, right? And then what you're going to do is you're going to chop these numbers in half. Okay, so you're going to take the first half of the numbers a0 up to a of n over 2 minus 1. Okay, and then you're going to take the second half of the numbers, which starts at a of n over 2 and goes up to a of n minus 1. Okay, so this thing over here goes from a0 up to a of n over 2. Oops. N divided by 2 minus 1. Okay, and the rest of it starts at a of n over 2 and goes up to a of n minus 1. Okay, and now what we're going to do is match up corresponding values like this. Okay, so we're going to match up the first value from the first half with the first value from the second half. Okay, you're going to match up the second value from the first half with the second value from the second half. Okay, and so on, and then you're going to match the last value from the first half with the last value from the second half. Okay, so that's what we're doing over here. We're matching up these values, right? A0 gets matched to a of a sub n over 2, right? A1 gets matched to this thing, to the next element, and so on. All right. So after you do this matching, then suppose you compute the min of each of these pairs. Okay, so you take whichever one's smaller. Okay, and then you do the same thing over here, and so on. Okay. So that's going to produce a sequence of n over 2 numbers, and you're going to call that sequence S1. Okay, and then you're going to take the same matching, right? But now you're going to take the max of each pair of numbers. Okay, so that's also a sequence of n over 2 numbers. You're going to call that S2. Okay, and now the claim is that both S1 and S2 are so if the original sequence is a bitonic sequence, then the claim is that S1 and S2 are also both of them are bitonic sequences, and furthermore, all of the elements from S1 are going to be less than all of the elements from S2. Okay, so that's the claim. Okay, so we're going to prove this claim on the next page, but first let's just say that this operation here, okay, where you split the list in half and then you do the min for one part and then the max for the other part. Let's call this a bitonic split. okay, because now you get two sequences, each of half the size. All right, so now let's prove this claim. So we're going to do a proof by picture, okay? So what I'm going to do is first, so we start with a bitonic sequence, okay? And then I'm going to split this down the middle. So the blue part is going to be the first half of the sequence, and then the red part is the second half of the sequence, okay? And so this is a bitonic sequence, so it increases in the first part and then decreases, okay? And let's say that when you cut it down the middle, this is actually in the decreasing part. All right, so now we want to do this operation where you match up values from the first half and the second half, right? And then either you take the min or the max. Okay, so the way we're going to represent this with the picture is that we're going to take the second half and just move it to the left. Okay, so we're going to, so that's what's being shown on this second figure over here, right? So we've taken the entire second half and moved it to the left. And when you do that, you're going to match up the corresponding values from the first and second halves. Okay, like so for example here, right, you have the first value from the first half. Okay, and this is being matched to the first value from the second half. Okay, and so on, right? The second value matches with the second value. Okay, so once you do this movement thing, then we've sort of done the matching that's required for this bitonic split. Okay, and now you know, these two parts, the blue part and the red part, so let's say that they cross somewhere. Okay, so they cross right over here. Okay, so now remember that the way you form this bitonic split is you either take the min of each pair of numbers or you take the max. Okay, now when you take the min, what's going to happen is, so for example, we match up these two numbers. And if you take the min, then you're just taking the lower of these numbers. Okay, so you're taking this number, right? And then over here, right, again, you after you match them up, you take the min, and so that is the lower number. Okay, so you see that given this matching, when you take the min, then for everything starting from this value all the way up to where the red line and the blue line intersect, okay, all the way up to that intersection point, when you're taking the min, you're just taking the blue part, right? Because the blue part is the smaller part up until the intersection point. Okay, and then after the intersection point, when you take the min, right, then you need to take the red part, because the red part becomes the smaller of the two values after the intersection point. Okay, all right, and then for the other one where you want to take the max of these two values, right, then before the intersection point, you want to take these red values, right, and then after the intersection point, you want to take the blue values. Okay, these blue values over here. Okay, so then then these two sequences that you form, S1 and S2, S1 is the min of the matching values, and that, as we said, is just going to be you know, you take the bottom part of this. Okay, right? You take the blue part up to the intersection point, and then you take the red part. Okay, and then the max of those two values is you just take the top half over here. Okay, so that pictorially is what this looks like. Okay, and now you see that both of these sequences are bitonic. Okay, so S1 is bitonic because you know, it increases up to this intersection point and then it decreases. Okay, and then S2 is bitonic because so here the blue part, right, you have an increasing part and then it starts decreasing, and then once you get to this value, right, so this red part here, okay, so this is actually the so this red part is the beginning of the red part over here. Okay, and this is also this red part over here. Okay, so basically what I'm saying is that if you look at this value, okay, so let's call this value x and let's call this value y. Okay, so then here you got x and then here you got y. All right, and we know that x is larger than y, so this x here is going to be larger than this y. And so this thing is actually equal to a bitonic sequence, but a shifted bitonic sequence, because you can take this y stuff over here and you can paste it after x, and then you'll get an increasing sequence followed by a decreasing sequence. Okay, so anyways, S2 over here is also a bitonic sequence. All right, and the last part of the claim was that everything in S1 is less than everything in S2. Okay, or less than or equal to everything in S2. And this is true because everything in S1 is going to be less than or equal to this, let's call this intersection point, let's call that X, okay? So everything in S1 is less than or equal to X, right? And everything in S2 is larger than or equal to X, okay? So therefore, all of S1 is less than or equal to all of S2. Okay, so that shows the this main claim about forming a bitonic split out of a bitonic sequence. Okay, so once we have this operation of bitonic split, then we can get started with our bitonic sort algorithm. Okay, so we're gonna define one more thing called bitonic merge. Okay, so the bitonic merge operation is going to take a bitonic sequence, okay, and then it's going to convert. This is like an increasing followed by decreasing sequence, okay, or rotation of one, and it's going to take this bitonic sequence and convert it to a completely sorted one. Okay, so bitonic sequence is not quite sorted, right, because it can increase and then decrease. Okay. But the bitonic merge is going to take one of these bitonic sequences and convert it to a completely sorted sequence. And it's going to do this using a sequence of these bitonic splits. Okay, so the way it works is that now the property about the bitonic split is that so the input to the bitonic split is a bitonic sequence. And then after you do the split, we know that the first half of the values is all going to be less than the second half of the values, right? So that's the property of the bitonic split. And you can see that this is kind of a sorting of S, okay? Because now you've taken this bitonic sequence S and you split it into two parts consisting of the smaller half and the larger half. Okay, so each of these halves is maybe not sorted, okay? But at least you've sort of sorted the two halves. Right, so the left half is completely less than the right half. Okay, so once you do this, right, then you can take each of the halves of S, right, and then so we're guaranteed that each of the halves is also bitonic. Right, that's the other property of the bitonic split, is that not only is the first half less than the second half, but both halves are also bitonic. So if both halves are bitonic, right, then we can apply the split again, right, to both halves, and then we get another sort of kind of like a sorting of both halves. Okay, so if you take the first half and you do another bitonic split, right, now you get these quarters, and the first quarter is going to be completely less than the second quarter. Okay, so that's kind of like a sorting of these two quarters. Okay, and the same applies for the second half. Okay, so let's right, and then you just keep doing this recursively. Okay, so so each time you do a bitonic split, it's kind of like you've sorted the sequence a bit. Okay, you split this into two parts where the first part is completely less than the second part. So we're just going to keep doing this until eventually we get down to a sequence of size 1. Okay, and when that happens, then we have that the entire sequence is sorted. Okay, so let's do an example of this. Okay, so suppose that we start with a a bitonic sequence like this. Okay, so it's a bitonic sequence. So in fact, I've marked out the increasing part and the decreasing part. So the increasing part is blue, and then the decreasing part is red. Okay. Okay. So then we're going to do a bitonic split on this. And the bitonic split is we're going to match up, we're going to split this thing in half, right, the sequence in half, and we're going to match up the corresponding values. Okay, so the 3 gets matched to the 95, right? The 5 gets matched over here, and so on, right? And then for each of these, we're going to take either the min or the max, okay? And what that's going to do is that's going to produce this sequence on the second row over here, okay? So you see that basically if you take if you take, like, for example, these two values, okay, and you take their min, right, so the min goes in the left half and the max goes in the right half, okay, so actually here nothing changed, okay, and then if you do the 5 with the 80, then actually again nothing changes, okay, so the 5 stays here and the 90 stays over there, okay, So for all of these pairs, basically nothing changes except for the final pair where you match the 20 and the 0. So then the 0 gets put over here, right? It's because it's smaller, and the 20 gets put over here. Okay. All right, and now you can check that everything on the left here. So this is going to be the first part of the bitonic split, right? So this is like the S1 part. Okay, everything over here on the left is less than everything over on the right. Okay, and furthermore, you can check that both of these parts, S1 and S2, they're both bitonic themselves. Okay, because for example, S1 here, right, it's increasing from 3 up to 14, and then it's decreasing. Okay, whereas here the S2, right, it's decreasing and then increasing, but this is just the rotation of a simple bitonic sequence. All right, so now we're going to do a bitonic split on both halves. Okay, so we're going to do 2 bitonic splits. So that means that we're going to match up the 3 and the 10, right? And you're going to put the smaller one on the left and the bigger one on the right. You match up these two guys, right? Match up these two and then match up these two. Okay, so you see that after you do this, right, we're going to get 2 sequences over here, right? This one and that one. And you can see that the left sequence, everything in the left is less than everything on the right. Okay, furthermore, the left sequence is a bitonic sequence, and the right thing is also a bitonic sequence. Okay. Likewise, we are going to do the same thing on the right over here, right? So we match up these 2 things, right? So now the 35 goes on the left and the 95 goes on the right, right? You do it over here, you have to swap them and so on, okay? And then you also get that all of these values are less than all of these values, okay? And furthermore, these sequences are bitonic, okay? So I've again labeled, how they're bitonic, right? So it increases here and then decreases, and then increases, decreases, and so on. Okay, and then we're going to take each of these bitonic sequences. So now we have 4 of these, right? We're going to take each of them and then do another bitonic split. Okay, yeah, and then you just keep doing that. Okay, so if you keep doing that, you're always putting the smaller values on the left and then the bigger values on the right. So then at the end, you see that we're going to end up with this thing over here. Okay, and this is indeed a sorted sequence. So that's the bitonic merge operation. Okay, it starts with this original bitonic sequence, right? You keep doing these bitonic splits on there over and over, and eventually you end up with a sorted sequence. Okay, now turns out that this bitonic merge operation, you can do this in parallel. Okay, and the way you're going to do it in parallel is that we're going to build it out of these circuits. Okay, so we're going to create this thing called a merging network. So the way this works is that in order to do the bitonic merge, we just need to do bitonic splits. And to do bitonic splits, all you need to do is just take 2 values and then either take their max or their min. Okay. All right. So then we're going to build these. We're going to represent that using these like little circuits over here. So these circuits are going to have 2 inputs, right? And then if we want to put the min on top and the max on the bottom, so they have 2 inputs and then 2 outputs, okay? So the 2 outputs are going to be the min of the 2 values and the max of the 2 values, right? And then you can have them in either order. If you put the min on top and the max on the bottom, right? So let's draw it this way with sort of this little plus here, okay? This plus is kind of indicating that this is being sorted in increasing order, right? Because it's first of all the min value and then the max value. Okay, or if you want to sort this in sort of decreasing order, okay, so you put the max value first and then the min value, right? You can draw this with a little minus here. Okay, so we have these basic circuit elements, and now if you want to implement a bitonic merge, then we just have to have lots of stages of these bitonic splits. Okay. So each of these things in the box, okay, represents a stage of the bitonic split. Okay, so each of these boxes represents basically one of these rows in this example over here. Okay, so for example, in the first bitonic split, right? So we have the sequence over here, and you need to match the first value with the the medium value, right? The value in the middle. Okay, and the second value with the middle value plus 1, and so on. Okay, right? So we match those values, and then we want to put the min on top and the max on the bottom. Okay, so that's exactly, so now we're going to use these circuits to do that, these little plus circuits. Okay, that's what this is indicating. So 3 and 95 get matched, and you put the min value up top and the max value, so the min value is going to go over here, right? And the max value is going to go over here. Okay, likewise, you match this 5 with the 90, and then you're going to put the min value over here and then the max value over here. Okay, and then you do the matching for all of these pairs. Okay, so that is the first bitonic split stage. Okay, now after you do that, right, then you're going to have that this sequence over here is a bitonic sequence, and this sequence is a bitonic sequence, right? And we said that you wanted to do a bitonic split on the first sequence and another one on the second sequence. Okay, and so to do that, right, we need to take the first sequence, and you're going to take the first element and match it with the middle element of the first sequence. Okay, and the second element with the second element. Okay, yeah. So then you do these matchings, and then again you put the minimum value up top and the maximum value on the bottom. Okay, so you use again you use this circuit over here. Okay, and then you do the same thing on the bottom over here, right? You do another bitonic split on the bottom. Okay, so then after you do that, you're going to get 4 bitonic sequences, right? So like this one, and then this one, and then this one, and then that one, right? And then for each of these sequences, you're going to do another bitonic split. Okay, so this is going to be the bitonic split on the first sequence, second sequence, and so on. Okay, so you just keep doing this. Okay, so you can see that at any stage, all you need to do is to compute this bitonic split, and then you can do that pretty simply just by just using these basic circuit elements. Okay, and now if you look at each stage, okay, all of these operations can be done in parallel, right? Like the operation between 3 and 95 is going to be done in parallel with the one between 5 and 90, right? Between 8 and 60 and so on. All of these are done in parallel. So therefore, this first step over here just takes sort of unit time, unit parallel time. Okay, and the second stage can also all be done in parallel. So this just also takes another unit time. Okay, so every stage can be done in parallel. Okay, and there are log n stages because because the size of the list keeps decreasing by a factor of 2, and eventually when you're down to just a single element, then the list is sorted. Okay, so basically we can do this bitonic merge in order log n parallel time using a bunch of these circuit things. Okay, so now we are almost done with bitonic sort. So just a few more steps, and then we will have the bitonic sort algorithm. Okay, so up to now we have the bitonic merge algorithm. Okay, so finally, we're going to take the bitonic merge and then use this to implement bitonic sort. And the thing about so the first thing to notice is that bitonic merge, so currently we're sorting this into increasing order. Okay, but you can just as well sort this into decreasing order, right? That's, you just flip the min and the max. Okay. All right, so then we're going to call this bitonic merge into an increasing sequence. We're going to write that like with the sort of plus sign over here, okay, the BM plus, okay, and then into a decreasing sequence, we're going to write that with the minus, okay. All right, now suppose you're given an arbitrary sequence and you want to sort it, okay. Then what we will do is first we're going to convert this arbitrary sequence into a bitonic sequence, okay. Right, and then where each part, the increasing part and the decreasing part, are both going to have size n/2. Okay, and then we're going to do a bitonic merge on these two sequences. Okay, so sorry, on this entire bitonic sequence. Okay, so there's just one sequence here. Okay, so again, you take your arbitrary sequence, you convert it into a bitonic sequence where the increasing part has size n/2 and the decreasing part has size n/2, and now you do a bitonic merge on this bitonic sequence. Right, and that is going to produce a completely sorted sequence. Okay, so that's the bitonic merge algorithm. Now, the only thing that we don't know how to do is how do you take this arbitrary list and convert it into a bitonic sequence? Well, to do that, what we're going to do is just take this list and then divide it in half. Okay, and then you're going to sort the first half in increasing order, and then you're going to sort the second half in decreasing order. And now you have a bitonic sequence. Okay, but the problem is, how do you sort the first half in increasing order, or the second half? Okay, well, you can do this recursively. Okay, so so overall, right, we're given an arbitrary sequence. What you're going to do is you divide this in half, right? You're going to sort the first half recursively, sort in increasing order. You sort the second half recursively in decreasing order, and then you do a bitonic merge on this overall increasing decreasing sequence. Okay, so that is the entire algorithm for bitonic split, bitonic sort. Okay, so let's look at a sort of a pictorial representation of this. Okay, so suppose you're trying to bitonic merge, bitonic sort on 16 numbers over here. Okay, yeah, so the first thing you do is you split the 16 numbers into 8 numbers into 2 parts with 8 numbers each. Okay, you're going to sort each of these 8 numbers first in increasing order, right? So this is the increasing sort, and then you're going to sort the other part in decreasing order. Okay, and then you're going to do a bitonic merge on this, and for the merge, you're going to merge them into increasing order. Okay, now the question is, how do you sort 8 numbers into increasing order, right? Well, you're going to take the 8 numbers, you break them into 4 numbers and then 4 numbers, and then you sort the first 4 numbers in increasing order, and the second 4 numbers in decreasing order, right? And then you do a bitonic merge on these 8 numbers. Okay, so this is this is sort of unrolling the recursion for you. Okay. All right, so then in total, you see that there are going to be log n bitonic merges, right? Because you have to keep doing this until you're down to lists of size 1. Okay, so each bitonic merge, we said, was being done in parallel using this bitonic merge network, and that took log n time. Okay, and there are log n bitonic merges in total. So therefore, everything can be done in log squared n time, log squared n parallel time. Okay, so bitonic sort takes log squared n parallel time. Okay, so that's the algorithm. The final thing I want to mention is that, well, this is not an efficient, a work efficient algorithm because, to do this, you need n processors. And so the total work you're doing is going to be n times log squared n. All right. Whereas, for sequential sort, you can do this in n log n time. So it turns out that it is possible to build, so these things are called sorting networks that we built. Okay, so the sorting networks are, they're built out of these little wire configurations over here, right? So they're built out of these little mini networks, which either just sort into increasing order or decreasing order. Okay, so you string a bunch of these together into a network and use this to sort. So these sorting networks, so currently the bitonic sorting network, okay, it is doing n log squared n work, which is not efficient, but it turns out that there are sorting networks which are work efficient. Okay, so for example, there's this thing called the AKS network. This is going to do just n log n total work. However, it's a pretty complicated algorithm, and furthermore, it's not practical because even though it does, asymptotically, it does n log n work. There's a huge constant in front of this network. Okay, so it's like a huge constant times n log n, and that constant is so large that this is simply not a practical network. Whereas bitonic sort, right, this bitonic sort network, this actually is highly practical. Okay, even though it's not work efficient, it's actually very it works very well in practice. Okay, so that's a bitonic sort. Now, the final thing we're going to talk about is sample sort. Okay, so sample sort can be used in a distributed memory setting. You can also use this in a shared memory setting, but typically we think of using sample sort in a distributed memory setting. Okay. So for the previous algorithms, right? So for the radix sort and the merge sort and the bitonic sort, those we tend to think of in the shared memory setting. Okay, so the way this works is suppose you're trying to sort n numbers using p processors. Okay. Now, ideally, all the processors are load balanced, so each of the processors is going to handle n divided by p values. Okay, so that would be the best case situation. Okay, so then how can you achieve this? Well, one thing is, suppose you pick p minus one values. We're going to call them pivots. Okay. And let's say the pivots are, so the values are going to be t1 up to t of p minus 1, okay? And then also we have two more pivot values, t0, which is equal to the minimum input value, right, little m, and then tp, which is the maximum input value, okay? Now we're going to use these pivots to form p buckets, okay, where the ith bucket contains all of the inputs between t of I minus 1 and ti. Okay, so let's say that you have a bunch of numbers here, okay? Okay, so we're going to pick up a few of these pivots. Oops, sorry. Okay, so we have a pivot which is equal to one of these smallest values, right? So this is a pivot, right? And let's say that you got a pivot over here, right? And let's say you got a pivot over here, right? T2, and then you got a pivot over here, okay? T3. Okay, so you see that so we have p plus 1 of these pivots in total, and you see that these values are going to cut all of these values, these input values, into p buckets. Okay, where the ith bucket, right, these are all the values between like t1 and t2, right, and these are all the values between t2 and t3. Okay, we don't assume that each of these buckets is sorted. However, we do assume that all of the values over here. Oh, right, and I forgot to say that all of these pivots, right, suppose they're sorted, okay? And so that would mean that all of the buckets in this third bucket over here, right, all of them are larger than T2, and so therefore they're also larger than all of the values in the second bucket, okay? And the second bucket is larger than all the values in the first bucket. Okay, so we're going to pick these p pivots. They're going to divide all of the inputs into p buckets, right? And then we're just going to sort each of the buckets. Okay, so yeah, and then after doing that, you get an entirely sorted sequence, right? Because we already know that the buckets themselves are between the buckets, like the second bucket is completely less than everything in the third bucket. Okay, so between buckets or at the bucket level, things are already sorted. Okay, so now all we need to do is sort within each bucket, and then everything becomes sorted. Okay, well, how much time does this take? So if you let S be the maximum bucket size, okay, then sorting is going to take you S times log S, S times log S time. Because, we have P of these buckets, right? The biggest one of them is going to be size S, and then we can sort all of these buckets in parallel using our P parallel processors, right? And each of the sorts takes S log S time, and so in total, we're taking this much time. Parallel time. Okay, so now this is going to work very well if all of these buckets are about the same size. Okay, so in fact, in the ideal situation, everything is exactly size n divided by p. Okay, so then it works. Yeah, so then all of the processors are perfectly load balanced when they sort within each bucket, and then this approach works well. Okay. However, the problem is that it's unlikely that the buckets are going to be the same size. Okay, so for example, if you pick just pivot elements randomly, then it's then the largest bucket size is quite likely to be not n divided by p, but it's going to be n divided by p times log n. Okay, so it's larger than this ideal size by a factor of log n. And then if you sort, sort this bucket, right, the largest bucket, right, so this is going to take you S log S time, and that's basically going to be n times log squared n divided by p time. Okay, instead of if everything were the same size, then the total time it would take is going to be n log n divided by p. Okay, so this is too large by a factor of log n. Okay, so right. Oops. Yeah. Okay. Okay, I should have put some animation here. All right, anyways, yeah, so if we just naively pick p pivots, then this algorithm is not going to work so well, okay? However, the sample sort algorithm is going to do things slightly differently, and the goal for sample sort is to make the buckets have approximately the same size. So it's going to even out the bucket size, okay? In fact, the sample sort algorithm is going to guarantee that the buckets are all going to be on the order of n divided by p, okay, with high probability. So sample sort is a randomized algorithm, okay? So it does certain random operations. So it's not going to guarantee absolutely that we end up with buckets of this n divided by p size, but it's going to guarantee that based on the random choices, then with very high probability, we're going to end up with even buckets. So the way it works is that instead of just picking p pivots, we're going to pick more than p pivots, okay? In fact, you're going to pick lambda times p pivots for some factor lambda, which is larger than 1, and which I'll show you later, okay? So we're going to pick more pivots, and then let's see. Okay, so we're going to sample all of these lambda p pivots, and then we're going to sort them, okay? And then we're going to pick every lambda sample from the sorted sequence. Okay, so that will produce p pivots. That'll produce p numbers, right? Because you have lambda p values overall, and then you pick every lambda value out of this, so that's going to produce p pivots. And then we're going to use those pivots that we picked, right? Every lambda sample, we're going to use those to form the buckets. And then we're going to do everything the same as before. Okay, so the only difference for sample sort is how we select these pivots. Right, we select it by, first of all, picking lambda p random elements, and then you sort them, and then you take every lambda sample as a pivot. Okay, now the claim is that this is going to produce much more even pivots. So more precisely, suppose we pick lambda to be this value. Okay, so it's going to be 12 times log n. Right? Then the claim is that no bucket is going to be larger than 4 times this optimal size, 4 times n divided by p, okay, with probability at least 1 minus 1 over n squared. So if you have a lot of elements, right, then if you pick lambda to be basically log of the number of elements, right, then we can guarantee that within a factor of 4, you get perfectly balanced buckets, and this happens with very large probability very close to 1, right, because your n is going to be large. Okay, so I'm not going to get into like sort of the proof of this. So the proof uses something called Chernoff bounds. Okay, so this is going to so Chernoff bounds are a very useful technique in the analysis of randomized algorithms, and it basically lets you bound the probability that when you add a bunch of random independent random variables together, okay, you expect that the sum of these is going to be equal to the expectation, right? The expected sum is just equal to the sum of the expected values of the random variables, okay? So the Chernoff bound lets you bound what is the probability that you do not get this expected value, okay? It's going to be a low probability, right? It's unlikely that you deviate from your expectation. And this Chernoff bound is going to say that there's this exponentially small probability that you deviate from your expectation, right? And using this Chernoff bound, you can prove this this theorem over here. Okay, so if this is true, right? So we're just going to believe this theorem, okay? But if this theorem is true, then since all of the buckets are balanced, right? Then when you run the sample sort, every processor is going to be sorting about the same number of elements, and so every processor is going to run in basically this much time, okay? And this happens with this high probability that comes from the Chernoff bound, okay? Right, and this algorithm also has low communication complexity because basically all we need to do is we need to broadcast the pivots, and then we need to somehow collect the buckets at the end. Okay, so let me just show you all the details of this algorithm. Okay, so initially the values, so we have n values, and they're just distributed in some arbitrary order on the processors. Okay, but each processor has n divided by p arbitrary values. All right, And now we want to pick lambda p random elements in total. So therefore, we have each processor pick lambda random values. Okay, and let's say that they all send this to processor 1. Okay, and then processor 1 is going to receive these lambda p values, and then it's just going to sort them. Okay, and then it's going to take every lambda value from the sorted sequence, and it's going to use those as the pivots. And so, so processor 1 needs to tell all the other processors about these pivots. Okay, so it's just going to take the set S of every lambda value. It's going to broadcast that set to all the other processors. Okay, and now all the processors have these pivots, and now they can use the pivots on the values that they currently have. Okay, so they each have n divided by p values, right? So they're going to use these pivots to break these n divided by p values into p buckets. Okay. All right, and then next, what we're going to do is each processor is going to be, so we have p processors, and each one of them forms p buckets. But ultimately, what we want is for each processor to be responsible for one bucket. Okay, so for example, if we have, let's say, 3 processors. Okay, so processor 1 has 3. Oops, draw this a bit nicer. So processor 1 has 3 buckets, right? Processor 2 has 3 buckets. Okay, and processor 3 has 3 buckets. Okay, so now ultimately we want processor 1 to take the first bucket from all of these guys. Okay, so then that's going to form one big bucket for processor 1. Right, so this is processor 1. Okay, processor 2 is going to take the second bucket from all these guys. Okay, so that's going to be his big bucket, right? And then same for processor 3. And what we know, so since all of these buckets were formed by these same pivots, okay, by these lambda values, okay, then using the previous theorem that we had, we have that all of these buckets that P1, P2, and P3 end up forming, they're all at most size 4 times n divided by p with high probability. Okay, and now we just have each process sort its own bucket, okay, locally, and then we're done. Okay, and then the overall sequence is well, since P1 has the smallest, so all of these come from the first bucket, which is like the smallest bucket, and then this has been sorted, right? And this is the second smallest bucket, which has been sorted, and so on, right? Then if you just read the values from left to right across all these processors, then that is the overall sorted sequence. Okay, so yeah, so just to do an even more concrete example of this. Okay, so suppose that initially we have so 3 processors, right? They each have n divided by p values, and they're going to pick lambda values out of those. Okay, so let's say they pick 2 values. Okay, so then they pick these 2 values, and they all send it to the to processor 1. Okay, and then processor 1 is going to take these values, and he's going to sort them locally. Okay, and then he's going to take every lambda value. Okay, so he takes 2 of these values, right? So the 8 and the 17, and then he's going to send these the 8 and the 17 to all of these other processors, and these other processors are now going to break things into buckets based on the 8 and the 17. Okay, so for example, the first guy, he's going to form this bucket, right? So this is everything less than 8, right? And then this bucket, and then the final bucket, right? This guy is going to form the so this is going to be his bucket 17. Okay. Right, so this guy is going to form, P1 is going to form these 2 buckets, and then, and then P2 is going to form, what do we have over here? We have these buckets, okay? Right, and then we're going to collect the first bucket, right, or these fragments of the first bucket, okay? So we're going to collect all this stuff, where is it? Okay, and then send it to processor 1. And then processor 1 will locally sort. Okay, so when he locally sorts, you're going to get this thing over here. Okay. Likewise, you're going to take the second bucket from each processor, right? And you're going to send it to processor 2. Okay. And then he's going to locally sort, and then he's going to end up with this part over here. Okay, so the only communication, yeah, so that's the entire algorithm, and we see that there's actually very little communication because the only thing you need to do is you need to send lambda p values, right? So this processor 1 is going to do a gather for lambda p values, right? And then he's going to do a broadcast for lambda values, right? And then in the end, we need to collect these buckets, okay? But these buckets are load balanced, and so there's not too much. So that's also not a high cost for that part. Okay, so that's the last sorting algorithm. All right, so that's the end of the lecture, and I'll talk to you guys next time.